Welcome to Understand the Math. In this Calculus 1 video, we're learning how to quickly and efficiently find derivatives of polynomials and exponential functions. We'll start by using the power rule to differentiate powers of x, then apply the constant multiple, sum, and difference rules to break down and simplify more complicated functions. Finally, we'll look at the natural exponential function, discover why e to the x is special, and practice using its derivative rule step by step. Be sure to download the free guided notes to follow along and try the examples for yourself. Let's start by looking at the power rule and walking through some examples. The power rule is a quick and powerful shortcut for finding derivatives of functions where x is raised to a power. The power rule is used to differentiate power functions, and these power functions look like this. F of x is equal to a constant times x raised to the nth power. We're going to start by first looking at the derivatives of some basic power functions. The first one will be to look at the derivative of the constant function f of x is equal to c. Notice from this graph that the slope of this function is equal to 0. That tells us that the derivative of any constant is going to be equal to 0. Let's now look at the derivative of a linear function, f of x is equal to x. The slope of this function is equal to 1, so the derivative of x with respect to x is just 1. Now what we're going to do is find the derivative of the general power function, f of x is equal to x to the n. To find what this derivative is equal to, we are going to start by looking at the derivative with respect to x of x squared. The way you take this derivative is you take the 2 that's up in the exponent, you pull it down in front, and then you multiply it by x, and then the power of x is going to be 2 minus 1. So you just subtract 1 from the exponent, and this gives us 2x. Let's now see what the derivative of x cubed is. We're going to do the same thing. We're going to take the 3, pull it out in front, multiply it by x, and then our power, we're going to subtract 1. So this gives us 3x squared. Let's do one more so that we can find the pattern. We're going to take the derivative with respect to x of x to the 4th. This is 4x to the 4 minus 1, which is 4x cubed. Now let's look and see what type of pattern we have. Notice that the exponent always comes out in front, and then the exponent that we're left with, 1, 2, and 3, is 1 less than the exponent that we started with. This tells us that the derivative of x to the n is going to be n times x to the n minus 1. And this is called the power rule. That is a really great rule to memorize. Let's look at some examples where we are going to use the power rule to differentiate each function. In our first example, we are given that f of x is equal to x raised to the 65th power, and we want to find the derivative. We're going to write this as f prime of x is the derivative with respect to x of x to the 65. Using the power rule, we are going to take the 65 that's in the exponent, pull it out in front, and then multiply it by x to the 65 minus 1. So you're going to subtract 1 from your exponent. This gives us 65x to the 64th power. And that's our derivative. Let's look at our next example. In this example, we have f of t is equal to 1 divided by t. Let's start by writing f prime at t is the derivative with respect to t of 1 divided by t. We can only use the power rule when our function is raised to an exponential. So what we have to do before we take the derivative is rewrite 1 over t in terms of t raised to a power. This is going to be d dt of t to the minus 1. See how we just now have t raised to a power? Now we can use the power rule. We're going to bring down the power, so we have a minus 1 times t, and then we're going to subtract 1 from our exponent. And this gives us minus t to the minus 2. And I'm going to write this answer then as minus 1 all over t squared. It's a really good practice to put your answer in the same form as the function that you're given. Let's now look at our third example. This one is g of x is equal to the square root of x. We're going to write the derivative as g prime of x is equal to derivative with respect to x of root x. To apply the power rule, we need to write the square root of x as x raised to a power. So we're going to write this as d dx of x to the 1/2. Now we can go ahead and apply the power rule. We bring down the exponent, and then we have x to the 1/2 minus 1. This is 1/2 x to the minus 1/2, which is 1 all over 2 times x to the 1/2. I'm bringing that power down in the denominator. Now then, let's write our answer as 1 over 2 square root of x, because we had a square root of x in our original function. And that's our final answer. Let's look at one more. For this one, we have the function y is equal to x to the minus 1/3. We're going to take the derivative, so we're going to write this as dy dx is the derivative with respect to x of x to the minus 1/3. Our x is already raised to a power, so we don't have to do anything more. Now we just have to apply the power rule. We'll bring down our exponent, minus 1/3, and this gets multiplied by x to the minus 1/3, and we're going to subtract 1. So this is minus 1/3 x to the minus 4/3, and that's our final answer. And it's in a similar form to our original problem. We're now going to learn about the constant multiple, sum, and difference rules and walk through some examples. These rules allow us to break complicated functions into smaller pieces, differentiate each piece, and then put them back together for our final answer. The first rule that we're going to look at is called the constant multiple rule. The constant multiple rule tells us that when we take the derivative of a constant times a function, all we have to do is pull the constant out in front and then take the derivative of our function. Let's now look at an example where we are going to apply this rule, and we're going to differentiate the function f of x is equal to 10 to the x squared power. Our derivative is f prime of x, and that is the derivative with respect to x of 10x squared. This is just 10 times the derivative with respect to x of x squared. You just pull the constant out in front. And then this is 10 times the derivative of x squared, which using the power rule is 2x. And this gives us a value of 20 times x. Let's now look at the sum rule. The sum rule tells us that when we're taking the derivative of two functions added together, all we're going to do is take the derivative of the first function and then add the derivative of the second function. Let's look at an example. In this example, we are going to differentiate the function f of x is equal to x to the fourth plus x to the sixth. Our derivative is f prime of x, and it's the derivative with respect to x of both of these functions, x to the fourth plus x to the sixth. Using the sum rule, we're just going to break this up, and this is the derivative of the first function, x to the fourth, plus the derivative of our second function, x to the sixth. Now all we do is apply the power rule to both of those functions, and our derivative of our first function is 4x cubed plus 6x to the 6 minus 1, which is 5. And there's our derivative. Let's now look at our last rule. This is the difference rule. It's really similar to the sum rule. The difference rule tells us that when we are taking the derivative of two functions that are subtracted, all we have to do is take the derivative of the first and subtract the derivative of the second. Let's look at an example. We are going to differentiate the function f of x is equal to x to the fifth minus x cubed. You might want to pause the video and see if you can do this one on your own. I bet you can. The derivative, f prime of x, is equal to the derivative with respect to x of x to the fifth minus x cubed. We're going to break this up. This is just the derivative with respect to x of our first piece, x to the fifth, minus the derivative with respect to x of our second piece, x cubed. This is then 5x to the 5 minus 1, which is 4, minus 3x to the 3 minus 1, which is 2. And there's our derivative. Let's look at some examples where we are going to use the power, sum, and difference rules to differentiate each function. Let's look at our first example. Our function is 2x cubed minus 3x squared minus 4x. Our derivative can be written as f prime of x is equal to the derivative with respect to x of 2x cubed minus 3x squared minus 4x. We are going to take the derivative of each piece, and whenever we have a constant, we can just pull that constant out in front of the derivative. So our first piece looks like this. It's 2 times the derivative with respect to x of x cubed minus 3 times the derivative with respect to x of x squared minus 4 times the derivative with respect to x of x. Now we're going to take our derivatives. Our first piece has 2, and then the derivative of x cubed is 3x squared. You just subtract 1 from the exponent, minus 3 times the derivative of x squared, which is 2x, minus 4 times the derivative of x, which is just 1. We can now write our answer as 6x squared minus 6x minus 4. When you get used to doing this, you can probably just write that answer down without going through any of these in-between steps. Let's now look at our second example. We are going to take the derivative of y is equal to x squared plus 4x plus 3, all divided by the square root of x. To use the power rule, we need each term in this function to be raised to a power, and we can't have a denominator. So let's start by rewriting this function and get rid of the denominator. This gives us y is equal to x squared divided by x to the 1/2 plus 4x divided by x to the 1/2 plus 3 all divided by x to the 1/2. We can split this up because we only have one term in the denominator. Let's now rewrite this. This is y is equal to x to the 3/2. I got that because we can think of 2 as 4 divided by 2, and then we just took 4 and subtracted 1. And then for our next term, we have 4x to the 1/2. This is just 1, and then we subtracted 1/2. And then our last term is 3x to the minus 1/2, just bringing that 1/2 up on top. Now we can go ahead and take our derivative. Our derivative is dy dx, and it is the derivative with respect to x of our first piece, x to the 3/2, plus our derivative with respect to x of our second piece, 4x to the 1/2. And then lastly, in our third piece, there is a 3 sitting there. We can pull that out in front and then multiply that by the derivative with respect to x of x to the minus 1/2. We could have also pulled out the 4 in the second term. Now we can take the derivative of all 3 pieces. Our first derivative is 3/2 x to the 3/2 minus 1. And then our next piece, we pull out the 4, and then we take the derivative, which is 1/2 x to the 1/2 minus 1. And then our last piece, we're going to take our 3, multiply it by minus 1/2. So we get minus 3/2 times x to the minus 1/2 minus 1. This then gives us 3/2 x to the 1/2 power plus 2x to the minus 1/2 power minus 3/2 x to the minus 3/2 power. Now, it looks like we could be done, but notice, let me pull this back down. Notice in our original problem, we had a square root of x. So that kind of clues us in that our answer needs to be in terms of square roots and not just in terms of x to the 1/2. So I'm going to rewrite this as 3/2 times the square root of x plus 2 all divided by square root of x minus 3 all divided by 2, and then x to the minus 3/2 becomes x to the 3/2 when we put it in the denominator, and then x to the 3/2 can be written as x times square root of x. Let me just make a note over here so this is clear. This is 1 over x to the 3/2, which we then wrote as x times the square root of x. And there is our final answer. The last example that we are going to look at is an application example. In this example, we are going to find equations of the tangent line and the normal line to the curve y is equal to 2x cubed minus x squared plus 2 at the point 1, 3. I'm going to start by finding the equation of the tangent line, and let's go ahead and let's write down what that equation looks like. That equation looks like y minus y1 is equal to the slope times x minus x1. The first thing that we need to do is find the slope. So the slope of our equation is the slope of the tangent line to the curve, and that is given by dy dx. And we want to find that at the point 1, 3. So that means x is equal to 1. So I'm just going to put down x is equal to 1. So what we're doing is we're finding the derivative at the point x is equal to 1. Let's write down what our derivative is. That is going to be the derivative with respect to x of 2x cubed minus x squared plus 2 evaluated at the point x is equal to 1. This is equal to 6x squared minus 2x, and then the derivative of 2 is 0, And we are going to evaluate this at x is equal to 1. So this becomes 6 minus 2, which is 4. So our slope is equal to 4, and we can plug that into our equation. We are given that x1 and y1 is the point 1, 3. So we can write this as y minus 3 is equal to our slope, which is 4, times x minus 1. Now, it's always nice to write this in slope-intercept form. So I'm going to bring the 3 to the right and multiply things out. This gives us y is equal to 4x minus 4 plus 3. And this gives us an answer of y is equal to 4x minus 1. And that is the equation of the tangent line to our curve at the point 1, 3. Now let's look at the second piece of this problem. We want to find the normal line. The normal line is perpendicular to the tangent line. So the slope of the normal line is going to be the negative reciprocal of the slope of the tangent line, which is minus 1 over m. So it's going to be minus 1 over m, which was 4. Now we do the same thing. Let's write down our general equation. Y minus y1 is equal to our slope. We'll go ahead and put in minus 1/4 x minus x1. Now we're going to substitute in that y1 is 3, x1 is 1. So this gives us y minus 3 is minus 1/4 x minus 1. Now let's multiply everything through. This is y is equal to minus 1/4 x plus 1/4 plus 3. Let's think of our 3 as 12 over 4. So our final answer is y is minus 1/4 x plus 12 over 4 plus 1 over 4 is 13 over 4. And let's highlight this because that is the equation of our normal line. We're now going to learn how to find the derivative of the natural exponential function and walk through some examples. We're going to start by looking at the graph of the natural exponential function. Here's the graph. The derivative of the natural exponential function is fairly easy to find because the slope of the function at the point x is equal to 0 is equal to 1. E to the x is the only exponential function with a slope of 1 at the point x is equal to 0. And that's why when you're studying calculus, you always start by finding the derivative of this particular exponential function. To find the derivative of f of x is equal to e to the x, we actually need to start with the limit definition of the derivative. That definition is f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x, all divided by h. In our next step, what we're going to do is wherever we have an x in the function, right here, we are going to replace that with x plus h. Let's see what this gives us. This is the limit as h goes to 0 of e to the x plus h minus f of x, which is just e to the x, all divided by h. Now we're just going to do a little simplification. Notice that we can rewrite e to the x plus h as e to the x times e to the h. That just kind of breaks it up. So this is the limit as h goes to 0, e to the x times e to the h minus e to the x, all divided by h. Now, each term in our numerator has an e to the x, so we can simplify it and pull that out. So we'll write this as the limit as h goes to 0, e to the x, and then we're left with e to the h minus 1, all divided by h. Now what we're going to do is take our e to the x and pull it outside the limit because it doesn't have an h with it. So this is e to the x times the limit as h goes to 0 of e to the h minus 1 all over h. Now what we're going to do is we're going to look back up to this line right there. What we have here is the same as what we have here if x were equal to 0, because e to the 0 is equal to 1. So this tells us that our derivative at 0 is our limit as h goes to 0 of e to the h minus 1 all over h. We're just plugging in that x is equal to 0. And notice that our left-hand side was f prime at x. So now we had f prime at 0. Now we can take this and plug it back in down here. And we're going to write this as e to the x times f prime at 0. Now what we have to do is go back up and look at our graph. The derivative of our function at 0 is the slope at 0, and that's equal to 1. So going back down again, we can say that f prime of 0 is 1, so our derivative is just e to the x. I think anyone that studies calculus needs to see that derivation. We can now say that the derivative of the natural exponential function e to the x is just e to the x. We are going to walk through some examples where we'll need to take the derivative of a natural exponential function. Let's look at our first example. In this example, we're asked for what value of x does y equal 2e to the x minus 2x have a horizontal tangent. I think the hardest part of this problem is trying to figure out what you actually need to calculate. So let's look at this again. For what value of x? So we need to find x where our function has a horizontal tangent. A horizontal tangent is going to happen where the slope of our curve is equal to 0. So that means we want to find x where our slope or our derivative dy dx is equal to 0. This means that the way we're going to start is by finding the derivative and setting it equal to 0, and then we're going to solve for x. Let's go ahead and let's take our derivative. Dy dx is the derivative with respect to x of 2e to the x minus 2x. This is 2 times the derivative of e to the x, which is just e to the x, minus the derivative of 2x, which is minus 2. And we need to set that equal to 0. Let's go ahead and let's pull the 2 over to the right-hand side. So this is 2e to the x is equal to 2. Dividing each side by 2, we get that e to the x is equal to 1. You may know by looking at a graph of e to the x that e to the x is going to be equal to 1 when x is equal to 0. If you don't know that, one way that you can solve this is by taking the natural log of both sides, because that will get the x out of the exponent. This then is x times natural log of e is equal to the natural log of 1. Then we have to know that the natural log of e is 1. So on the left-hand side, we just have x. And then we have to know that the natural log of 1 is equal to 0. So we get x is equal to 0. I have a video on the natural exponential and natural logarithmic function that you may want to look at if you're rusty on exponentials and logs. Let's go ahead and let's highlight our answer. This tells us that our curve has a horizontal tangent at x is equal to 0. I went ahead and graphed this curve just so that you can see this. Do you see that right here at this point, x is equal to 0, we have a horizontal tangent. Let's now look at our second example. For this problem, we are asked to find at what point on the curve y is equal to e to the x is the tangent line parallel to the line y is equal to 2x. Let's see if we can figure out what we need to do. We want to find at what point on the curve. That clues us in that we need to find x, so let's write that down. We want to find x, and we want to find x where the tangent line is parallel to the line y is equal to 2x. If two lines are parallel, that means they are going to have the same slope. So we're going to find x where the slope of y is equal to e to the x equals the slope of y is equal to 2x. Remember that the slope is the derivative of the function. So we can say that the derivative with respect to x of e to the x has to equal the derivative with respect to x of 2x. The derivative of e to the x is just e to the x, and then the derivative of 2x is 2, so we have e to the x is equal to 2. Now, we need to solve for x, and the way to get the x out of the exponent is to take the natural log of both sides. So this is natural log e to the x is natural log of 2. This is x, natural log of e is natural log of 2. Natural log of e is defined to be 1, so we have that x is natural log of 2. Now, let's go back up and look at what we were asked to find. We wanted to find what point on the curve. Normally, when you're asked to find a point, that means you need the x value and the y value. So let's see what our y value is. Our y is equal to e to the x. So this is e to the natural log of 2, and that's just equal to 2. So our point is natural log of 2, comma 2. That's our x value and our y value. I graphed both of these functions just so that we can understand our answer a little bit better. We found that the slopes were the same when y was equal to 2. That occurs right here, and that corresponds to this point about down right here, which is actually natural log of 2. Let's look at our next example. For this example, we are asked to show that the curve y is equal to 2e to the x plus 3x plus 5x cubed has no tangent line with slope equal to 2. Let's remember that the slope of the tangent line is the derivative. So we're asked to show that the derivative dy dx is not equal to 2. So there is no tangent line with slope equal to 2. Let's go ahead and let's take our derivative. Our derivative dy dx is the derivative with respect to x of 2e to the x plus 3x plus 5x cubed. We're going to break this into pieces. We can always pull the constants out in front. So this is 2 times the derivative of e to the x, which is just e to the x, plus 3 times the derivative of x, which is 1, plus 5 times the derivative of x cubed, which is 3x squared. So this is 2e to the x plus 3 plus 15x squared, and we need to show that that is not equal to 2. That's actually really hard to do. You know what is easier is if we can show that an algebraic expression is not equal to 0. So I am going to pull the 2 over to the left, and this gives us 2e to the x plus 3 plus 15x squared minus 2 is not equal to 0. We can combine the 3 and the minus 2 and write this as 2e to the x plus 15x squared plus 1 is not equal to 0. Now let's look at each term separately. E to the x is always greater than 0, so let's write that down. So this is greater than 0. X squared is greater than or equal to 0, so this is greater than or equal to 0. And then our 1, of course, is greater than 0. When we add these three terms, we get an expression that is greater than 0, and that tells us that it is not equal to 0. So we have shown that 2e to the x plus 3 plus 15x squared cannot be equal to 2. I actually took this expression right here and I graphed it because I wanted you to see that that expression is definitely greater than 0. And that's it. You've learned how to use the power rule, constant multiple rule, and some indifference rules to differentiate polynomial functions, and how to find the derivative of e to the x and functions involving e to the x. You've also practiced finding tangent lines and interpreting what the derivative tells you about the slope of a curve. To really master these skills, make sure you work through plenty of practice problems on your own.
If this video has been helpful to you, please consider subscribing to my channel. Keep believing in yourself and have a great rest of your day.